Hello guys, this is Hiten Shilar, and today we are going to talk about black holes. It has been a lot of days we haven't talked about black holes explicitly. So I know especially about black holes we haven't talked about. Uh, in my new book Hyperrelativity, which was published just a month ago, we are selling a lot of copies. People are really loving it, and so in my new book Hyperrelativity, we have talked about black holes, but a black hole is treated just like a special case there. The book is on relativity, but a black hole is just a special case there. But we haven't talked especially about black holes there. So in today's talk, let's cover black holes. So let's begin. So when you talk about black holes, some black holes like all yeah so black holes are formed by an implosion of a star. So how a star forms is like, firstly we have a gas cloud, and then gas cloud matter start to attract each other until they form some mass. Okay, mass energy density, and as that mass energy density grows, the nuclear fusion ignites. Okay, so the nuclear fusion follows, and after that heavier and heavier elements are created. Hydrogen is fused into helium, helium is fused to carbon, and then nitrogen, oxygen, and so on till iron. Now this nuclear fusion is basically just to maintain the surface of the star so that it doesn't collapse due to its under its own gravity, and that's the hydrophilic equilibrium. And so that nuclear fusion maintains that thing. Okay, so the maintains the surface of the star, as I said. So but there's a limit how much you can fuse these available atoms there in the star, and once you reach the iron, the heaviest of fusible material matter, once you reach the iron, then the nuclear fusion stops, and the tug of war between the hydrophilic equilibrium of a star and the gravitational pull of the star's material, in the ongoing tug of war, the ongoing tug of war is won now by the gravity. Once we reach at the iron, there's no material to fuse and create the opposing force, so we just got the gravitational force winning there. And then what happens? The entire core of a star, or the material of a star, collapse under its own gravity. And what we get is, based on the mass energy density of a star, we get white dwarf, we get neutron star, or we get a black hole. So in this video we're talking about black holes. So once the star is enough massive, like more than 3 solar masses or something, if I'm correct, yeah, exactly that number. So once it exceeds that mass limit, and then we already have a black hole. Now how should we imagine a black hole? So look, space-time is a four-dimensional manifold. Okay, so let's say we have a two-dimensional manifold instead. Now a hole in a two-dimensional manifold is a two-dimensional hole. Okay, so it has its length, it has its breadth. Okay, we call it radius, whatever we call it, but it's a two-dimensional thing. Okay, it has its length and breadth. Maybe it diameters, two diameters of a circle. So it's a two-dimensional thing. Now a hole in two-dimensional paper is two-dimensional. A hole in 3D space so is a three-dimensional sphere. But our universe is a four-dimensional space-time. So what is a hole in four-dimensional space-time? It is a four-dimensional hole. Yes, it is a four-dimensional hole. So a black hole is basically a four-dimensional hole. It's not just it's not just a hole in space, but it's also a hole in time. So a black hole is basically a four-dimensional hole. It's not just 2D, it's not just 3D, it's a four-dimensional hole. So yeah. So now let's talk about the event horizon of a black hole. So event horizon is nothing but a boundary in the space-time where if you lie, the escape velocity for you will be would be the speed of light. C, the speed of light. Now here on the earth we have the escape velocity as 11.2 kilometers per second. Now I have greatly explained in my book Hyperrelativity how staying on earth is just like same as traveling at 11.2 kilometers per second in space, Similarly, being exactly on the event horizon of a black hole is like traveling at the speed of light in space. I know special relativity will never allow it, but we are talking about general relativity. Maybe we can't say like you are traveling at speed of light. I'm saying it is light traveling at speed of light. Time stops for you. When you stop traveling in time, you move at speed of light in space. Greatly described in my book Hyperrelativity. So once you're at the event horizon of black hole, you get a perspective of light. Event horizon is bizarre, guys. Yeah, it is really bizarre. So once you're at the event horizon of black hole, it is just like traveling at sea in space. It's like traveling at speed of light in space. Yeah. Now many people ask me. This is the third question. Yeah, about black holes. That many people ask me, are we inside a black hole? Now I think no, because the universe is right now, as we can see, is following a FLRW model of cosmology, but that is not we find, you know, inside the black hole, the space between event horizon. I mean, whatever topology of space-time is, between the event horizon and the singularity of black hole, we don't find it there. So I don't think that we are inside a black hole, but it's kind of, a interesting view of having the entire universe inside a black hole, or the universe itself is a part of inside of a black hole. So if the universe is inside a black hole, then what is outside the universe is totally switched coordinates. So if we are inside a black hole, let's say we have the space as it is, time as what we feel like, then out of that black hole is what we have the same space-time continuum, but with totally different roles, a totally switched role space-time coordinates or continuum. Yeah, so it's interesting to visualize that. Also, let's talk about now the singularities. So a black hole, people mistook it singularity as a point in space, because once you fall into a black hole, you think like you're moving in space, but now the same space after the event horizon of black hole becomes time, and now what you were thinking as space becomes time. So it's a singularity in time. Okay, maybe as you look from our universe, in that perspective it may be just a space, but once you belong to the universe after the event horizon, we can also call it a pseudo universe. Once you belong to that universe, you have to follow the rules of space-time there. So now the space has turned into time, and so a singularity is just not a point in space, but it's a point in time there in such a pseudo universe, the universe just after the event horizon of a black hole we are talking about. So once we cross the event horizon, the singularity is not a point in space, it is a point in time. Yeah. So maybe with the point perspective of a universe is still a point in space, but once you go after the event horizon, you have to follow that rules of space-time in there. Okay, so it's a moment in time. The singularity is moment in time for you once you are inside a black hole, once you cross the event horizon of a black hole. Can a wormhole attaching a universe inside a black hole and the universe outside a black hole? So you get the question, I think. So if there is a wormhole, guys, that connects the universe outside and the universe inside a black hole, how would the travel be like? Well, it will be like, let's say we send two people, one from our normal side of the universe, and one guy from the inside the black hole is coming, in the normal to the normal universe. Now both of these guys come from both the ends. Now they meet like at the right spot where the travel hasn't, I mean, the one who is coming from a black hole has basically switched coordinates. As I said, the black hole has switched coordinates compared to the normal universe, and normal universe has switched coordinates as compared to the black hole universe inside the pseudo universe, the black hole universe, as I said. So as they come near to each other, if they meet at the right point where their space-time coordinates is are, where the space-time coordinates are haven't yet switched completely, then the moment they try to shake their hands, they can't really do so, because it would be more like a gravitational space-time interaction or space-time distortion instead of a physical handshake. Something I mean, they can't really physically connect with each other, because that's space-time distortion. That's going to always happen because they are in totally switched coordinates. It is also there in Interstellar movie when Cooper and Murph like handshake scene. They are trying to make a handshake, but that handshake was never physical. It was like a space-time distortion. The reason behind, because Cooper was inside a black hole, Brand was coming from the outside universe. They met at the right point where the coordinates were totally switched. One from the black hole, one from the normal universe, and their coordinates were like totally switched. And so it wasn't a physical handshake, instead it was a space-time distortion handshake. So yeah, so it's so yes, a wormhole, to answer the main question, a wormhole can connect a bridge. It can form a bridge, I mean, between the universe and the universe inside a black hole. Yeah. So many people ask me a question about black holes, whether we can form a black hole by dark matter. Look, how we form a black hole is like we have a particular set of mass, we have x amount of mass, and when we calculate the Schwarzschild radius of that particular amount of mass, and when we have that mass implode into that Schwarzschild radii, you just form a black hole. Every single mass can form a black hole. Every amount of mass can form a black hole once it's put it into its Schwarzschild radii. But now the thing is that for dark matter we need some external force, but for normal matter, stars are doing our work. So realistically speaking, in the present universe, we can't really have dark matter to form star, because we need external force for that. But in the present universe, as I said, the stars are doing our work. We need some mass energy density like stars, which can implode into a black hole. But dark matter can't form stars in the present universe. And I mean, to form a star, the the system of a star is a system which is what creates a black hole. But dark matter in the present universe can't form that system. So what makes a star system is all these four fundamental forces, which we have: gravitational force, we have electromagnetic force, then weak force we have, and also the strong force. These forces are responsible to make the star where it is, and we need a star in the present universe, not just a star, but a star massive enough to form a black hole. So along with this, so that's why in the present universe, when we form a black hole, we just not talk about mass density, we talk about mass energy density, because mass energy density is all about also the inclusion of these fundamental forces of the universe. And that's what's going inside the star. So a star as a system is needed in the present universe to form a black hole. But if you have dark matter and you apply some external force to it, and just put that mass of dark matter into its Schwarzschild radii, yes, of course you can create a black hole. Look, the only thing we have is mass, and we have to just put it into its Schwarzschild radii. That's what we have to do. And no matter you have mass of a normal matter or mass of a dark matter, it just doesn't matter. You just have to put it into Schwarzschild radii. Now the thing is that for dark matter we have to externally apply the force, and in case of normal matter we already have stars to do that work. So in the present universe, dark matter themselves can't form a black hole, but matter, we have been seeing it many times, through our telescopes, about stars, going to supernova and then suddenly fading off, and just nothing going on there. So they may be forming black holes. Yeah. So the stars are doing our work here, but dark matter apply some external force. Dark matter can't themselves form black hole. Very famous question: is a black hole a gate to the parallel universe? Yes, it can. If we have a white hole in some other universe and black hole in ours, connect the two singularities, we have a bridge between two universes. But that's very wild idea. Okay, so let's not talk about it. But something related I want to talk about, like if a black hole, you know, if a same black hole serves in between two universes. Let's say we have our universe, let's say we have a parallel universe. If the same black hole with two event horizons in both of this universe, we have a universe, let's say we have one black hole, okay, one black hole, the same black hole has two event horizons in both of these universes, then two people can actually meet, you know, within the black hole actually. So once we have that space time in between the event horizon and a singularity of the black hole, and since we have two mouths of that black hole, you know, as form of event horizon, the form of two event horizon that's been connecting the parallel universe and the normal universe, once we have that, and when people from different universes going there, they can meet each other in the space time inside a black hole. And yeah, so that's really an amazing way, maybe realistic way, near, and it's not as wild as having a white holes in some other universe connecting the singularity of a black hole from our universe, and then actually making a bridge and go there, you know. But okay, we can really meet two people from different universes can really meet each other, as I explained by how, you know. So yeah, so with that we are ending the black hole talk. And please check out my book Hyperrelativity. Hyperrelativity, the speed of light is the speed of existence. The book is available on Amazon and various marketplaces worldwide.